Hey YouTube, what's up, this is Link. Welcome back to another episode of Coding Session. So I finally got my problem of the week from the Leetcode Weekly Digest. Can't pronounce today. And that is the maximum binary tree 2. So you know what that means. There's been a problem before this, but let's actually challenge ourselves a bit and actually do the problem that was selected by Leetcode for us. So this is maximum binary tree 2. We are given the root node of a maximum tree, a tree where every node has a value greater than any other value in its subtree, and that is what a maximum tree is. Simply, every node has a greater value, has a value greater than any other value in its subtree. So for example, we have a tree of 4, 1, 3, 2, and we want to insert 5 into this tree. Well, since 4 is less than 5, and of course is less than all of these, it has to become the new actual root of this tree. So as you see, we want to insert it in this position, very first root of the tree. Over here we want to insert 3. 5 is less than 3, that's not true, and of course we're going to recur to the left and then to the right subtree. But remember, to keep the definition of a maximum tree, it's a tree where every node has a value greater than any other value in its subtree. The only place for 3 to belong is below 4, as we can see. And of course we want to insert 4 here. 5 is less than 4, that's not true. Recur to the left, recur to the right. 3 is less than 4, that's true, and then place it into that new root and that into that right subtree. So that's kind of the idea. Insert a node while preserving the maximum tree definition. So this question is quite interesting. It's a medium difficult question, but look at the like and dislike ratio. 197 likes versus 429 dislikes. There's so many problems I see on Leetcode with huge. This is just scratching the surface. I'm talking about that 500 likes versus 5,000 dislikes, or some crazy number like that. That might be over exaggeration, but it can go into the thousands with the like dislike ratio. So I don't understand why there's problems like that, and I can actually understand some problems. So some problems, I'm gonna tell you, are absolutely ridiculous. Unless you're going for the big N's, and if you don't know what the big N's are, they stand for the big name companies: Apple, Amazon, Google, etc., etc. Microsoft. That's what I was trying to say as well. But even so, there's some problems on Leetcode that are a little bit ridiculous. Sure, they're interesting, but they're a little bit ridiculous. But I think this problem is quite interesting, especially since we've been going over binary trees for the past 2 or 3 episodes. So let's see what we can do. So, like I've said in my previous binary tree episodes, most algorithms you are going to implement, or you'll even see online if you're studying binary trees, are going to be recursive. If you're not using recursive on binary trees, you're going to be in big trouble. So that means we need a base case. So if root is equal to null, we simply want to return new tree node reference of value, because the tree is empty. And that's still preserve the maximum tree rule, obviously. But now we need some other conditions. So remember when I said in this example, and all the other examples apply to, how 4 is less than 5, and we want to make 5 the new root and push 4 to its new left, or its new right. So let's go ahead and do that. If we do if root dot val is less than value, as we just explained, we want to create a new tree node reference node equals to new tree node of value node dot left. So the node left becomes the root, and the new root becomes the value, or the node we are inserting into our tree to preserve the maximum tree rules. Root is equal to node, and simply return node. So this is going to take care of that rule, trying our best to preserve the maximum tree rule, and we'll take care of the left subtrees. And now we want to also recur to the right subtrees, so we can simply just do root.right and do the recursive call, which is insert into max tree for root.right and val. And this should take care of the lefts. This will take care of the maximum tree rule as well as the left subtrees, and this recursive call is going to take care of it to recur through these subtrees, and then just return the root. So let's see if this works. Okay, so the first case works. What about the rest of the test cases? There we go. And of course, when it comes to recursion for binary trees, 0ms runs faster than 100% of the Java submissions online. So there you have it. Recursion at play when it comes to a binary tree problem. Of course, if it's empty, just return the value. That's still a maximum tree. But if the root value is less than the value you're trying to insert, you want to go ahead and make that the new root and push that old root to the left, and make the new root the node we are inserting, and then do the recursive call to go ahead and recur through all the trees, left and right subtrees, just like that, and then just return the root. So leave a comment down below if you want me to touch on any of these, any explanation. This problem is, I will admit, a little bit confusing. Maybe that is why there's a like and dislike ratio, and the gap is really huge when it comes to the likes, because there's more dislikes. And that's about it. So I mentioned in my traversal videos that there is something called tree rotations, and that is AVL trees. It's essentially a binary tree, except its idea is to keep it constantly balanced, or always balanced when you're inserting a new node. Unfortunately, AVL trees do get a bit complex. I can go over it with you guys with a document when I was in my data structures classes, and just go over it with you guys. There's many implementations online. I recommend Geeks for Geeks. They are the best when you want to go ahead and look at proof of concept data structure examples. But this is going to be left for another video, and that video is going to be quite long because there's AVL trees go really, really deep. So just wanted to mention that. So yeah, thank you guys for watching. Thank you guys for the support, and yeah, have a nice day. See ya.